Hi everyone, I'm Fabrizio from Nereos, and I'm going to present you a novel hyperspectral imaging system for low-light applications. Differently from common hyperspectral technologies, which are based on gratings or filters, our device is based on a patented Fourier transform approach. In Fourier transform approach, an interferometer is employed to create two replicas of the incoming light. By varying the delay tau between the two replicas, the intensity pattern at the single pixel detector, which is called interferogram, is measured, and the Fourier transformations provide the spectrum of the light. Now, if we extend this working principle to the bidimensional case by replacing the single pixel detector with a bidimensional one, a time domain data cube as a function of tau is recorded at the bidimensional detector, and Fourier transformations for each pixel of the image provides the final hyperspectral data cube. This is the experimental setup of our device, which is based on a birefringent common path interferometer with advantages in terms of compactness and stability, followed by a camera lens and a CMOS camera. The spectral range of the device is 400 to 1 micron region, but we are now developing the infrared version. The main advantages and differences with respect to push-broom approach is the steering technique employed. So the camera does not need to move during the measurement time with respect to the sample so that it is suitable for static objects. Also, the spectral resolution can be varied via software, and the fact that no slits nor gratings are employed enables the device to have a very high throughput and high sensitivity. In particular, this is a picture of the HYPERSPECTRAL model, which is the commercial device, showing the 1 cm clear aperture in the front face. In order to demonstrate the high sensitivity of our hyperspectral camera and the capability in measuring low light signal, we have decided to apply to fluorescence measurements. In particular, here on the left, you can see the RGB image of the sample that we measured, which are two leaves of a poinsettia plant, one green and one more reddish. On the right-hand side, you can also see the experimental setup in which a 2 watts LED at 400 nanometers excited the leaves, and the hyperspectral camera is placed on the top to measure the fluorescence emitted by the leaves. A long-pass filter at 500 nanometers was also employed in the detection to cut out the much more intense excitation light, and the overall measurement time was 50 seconds. Here you can see the final hyperspectral image. On the left, you can see the image plotted at 740 nanometers wavelength, which corresponds to the peak in the spectrum of the emitted fluorescence by the chlorophylls of the leaves. And on the right, you can see three different spectra corresponding to the 3 pixels highlighted in the image. In blue and in red, respectively, you can see the fluorescence signal emitted by the two leaves, and you can appreciate the differences by looking at the ratios between the peak at 690 nanometers and 740 nanometers. In yellow, you can also see the background signal. Also, I would like to highlight the really good spatial resolution of the image by showing a zoom in of one of the two leaves. Also, please note that the measurement time is independent on the number of the megapixels, so if needed, it is also possible to replace the CMOS sensor to increase even more the spatial resolution. To conclude, I would like to show you the first images in the infrared obtained with the first prototype of our SWIR hyperspectral camera. For this, we have decided to apply to food applications. You can see a measurement of an apple and a measurement of walnuts. In both cases, you can see on the left the RGB image, and on the right the clustered image obtained with the classification algorithm. In the first case, we were able to distinguish the bruised part from the healthy part of the apple, while in the second case, we were able to distinguish between different components of the walnut, namely the kernel from the shell. And on the bottom part, you can see the relative reflectance spectra in the infrared region. So thank you very much for your attention, and please do not hesitate to contact us in case of further questions.